podcast. This is Mr. White.
Mr. Johnson.
And today we're going to talk about projectiles. And we've got some video footage, do some play-by-play on some videos. And today we're going to do special cases. So, projectile. What's a projectile to you, Mr. Johnson?
Well, I'm kind of a history buff, and, projectiles are just something that are being fired.
Yeah. And actually, that's exactly, I always spell this guy's name wrong, Galileo. I don't know if that's right. Galileo's the guy that figured it out, actually. He wrote a book for the Roman Empire that figured out that if you launched something at some speed and at some angle, then it will land and hit the wall to knock the wall down.
So that's why their catapults were so accurate?
Yeah. They figured out the math of it first. Now, he did this without a lot of understanding, but he did understand this really important thing. Without knowing what it was, he understood the concept of gravity. And he understood that gravity acts on all objects in exactly the same way. So whether you're firing a bowling ball or a boulder or something that's on fire or a dead cow, as the case might have been, the object was still under the influence of gravity. It didn't matter how much it weighed or anything like that. So in your investigation today, you did a very specific launch angle. You did a launch angle equal to 0 degrees. So when I refer to launch angle, I'll write the Greek letter theta, because you'll see that for angles. You should have seen that in geometry, I think.
Was that like cosine and tangent and stuff?
Some of that trig stuff, yeah. So what you guys did is you had some pennies, all right? And one of them would just fall straight down. And the other one took this path that kind of looks like a half a parabola. Something we saw in math, right? A parabola. Wow. But we're only going to look at half of it today. So, Mr. Johnson, when they did these experiments with the pennies, I always found it interesting. When you look, what do you think you notice when you see them?
Well, at first glance, it kind of looks like they're falling at the same rate.
Yeah. So they're falling at the same rate. So when you look, and we don't always trust our eyes. That's why magicians make so much money.
Right.
What I do is I close my ears. I close my eyes, and I turn my ears on, and I just listen. And if they're going to fall and hit at the same time, you should hear. But if they're going to fall and not hit at the same time, you would hear.
Alternating sound.
You would hear an alternating sound. And the strange thing is, I heard them both hit at exactly the same time. And so when you think about all that, if they're hitting at the same time, they must be falling at the same rate. And it's because it's due to gravity. Gravity is that thing. It's acting on all objects in exactly the same way, regardless of how heavy it is, regardless of how fast it's moving out, etc.
I was going to ask. That one looks like it's moving pretty good because it gets some distance.
Yeah. So the Mythbusters, they do this experiment, and it was called bullet fired versus bullet dropped. I'm not a big Mythbusters fan, but they got this one right.
You got to think about mustaches, don't you? Don't like them?
Yeah, except the one I grow in the winter. But they do this experiment where they do all the high-end science and they get all the technology out, where they take a gun, another Mr. White classic drawing. That one's actually not too bad.
Yeah.
And the thought is a bullet is fired out and is still under the influence of gravity and will eventually fall to the ground. And it also kicks a shell out of the side of it. And the age-old physics question is which one hits first? And of course it's a loaded question because if gravity acts the same on all objects, then both objects hit at exactly the same time, which goes back to our penny experiment. This is your bullet fired. This is your bullet dropped. Yes, this is moving at a much higher rate of speed, but gravity doesn't know. Gravity just grabs and drags down. And so at the end of this podcast, there's a series of experiments that we did with our physics gun, and we show bullet fired versus bullet dropped on a much smaller BBCHS scale.
Right.
The other special case is a launch angle of straight up. So 90 degrees.
Okay.
So why is 90 degrees special? Any thoughts about that?
Well, it's exactly perpendicular to 0 degrees.
Sure. And so if we launch something up at a rate of 40 meters per second, we know that gravity is going to slow it down, and that it's going to travel slower and slower on the way up at each moment in time, until at the very top, it's not moving at all. Now, I've rounded. It should not be exactly 10 meters per second
Right.
difference,
you
right?
might- okay.
Because gravity is really,
9.8.
9.81. And then we notice that it starts to fall, and gravity acts on it. Not only does it slow the object down, it also speeds the object up in a uniform path. So at the first moment in time, it's going 40 up. Then in the first second, 30 up. Second, 20 up, 10 up, nothing. And then the next moments in time, seconds in time, 10, 20, 30, 40, down. So gravity is uniform.
Does that mean it's constant?
Yeah, it's constant. This is a kind of constant acceleration. It can't tell the difference if an object is heavy or light. It doesn't understand air resistance. It doesn't know about friction. It doesn't know about any of these things. What it knows is that it treats all objects in exactly the same fashion.
Now, when you say constant acceleration, are you talking both positive and negative?
It's only negative because you've never seen something fall up. Stuff falls down due to gravity. And so let's do some graphs. Always a big fan. I'm going to start writing y's instead of x's because we're talking about things that fall.
Okay.
Okay? And so then I got a vertical velocity and I've got a vertical acceleration. So if I've got an object, let's see, that is constantly accelerating due to gravity, well, it'd be a constant negative acceleration.
Okay.
If this is one of my pennies that has fallen off the table, it starts at 0 and it becomes more and more negative in its velocity. The last one is a little trickier. It all depends on what you want to call 0. Let's call the ground 0.
Okay.
And so what we would see, vertically speaking, is that it starts slow and finishes fast. So it would look something like that. If this is our penny flicked, or this is our penny dropped, our bullet dropped, or whatever, it doesn't matter. These are our graphs for 0 degrees launch angle. If I wanted to look at the x of this, okay, that's going to make some sense, but maybe not a lot of sense. These are all time graphs. If I'm going with my penny flicked, well, my penny flicked cruises along at a constant rate sideways, which means it's got a constant speed, which means there's no acceleration. On the Chapter 1 test, it was really frustrating to see students tell me that there was a constant acceleration and a constant velocity
Right.
simultaneously. Of course, that's impossible. So this is launch angle 0 for any projectile, whether it's a bullet or a penny or whatever the case is.
So based on these two graphs, what you're telling us is that not only is gravity affecting the penny that we either dropped or flicked, and it's going up and down, but it's actually moving horizontal as well?
It can be.
Okay.
So this, if we pretend that these aren't here, okay, This is just for any object that you've dropped off the edge of the table.
Okay.
If you shove it off the edge of the table, then we include the x-graphs as well.
Ah, okay.
Okay, so these were our special cases. If you wanted to talk about the 90-degree launch angle, well, that's not too difficult either. And for this one, for example, we only talked about straight up, straight down. So of course, that would be gravity's constant. We threw it up. It peaked and stopped. It's on its way down. We throw it up with a positive velocity. It peaks and stops. It comes crashing down. And there it is. So that's projectiles. That's 90 degrees in this case.
So that second graph, just to clarify, when it goes past supposed x-axis, that's when it starts speeding up again.
Yeah, it's stopped. So it slows down.
Okay.
And it stops right there, and then it speeds up. Now, if I had drawn better graphs, each of these points would correlate to points up here. So really, the peak of my graph should be there, and so on.
All right.
I believe that covers special case projectiles. We'll talk more about projectiles in Section 5.
All right.
So signing off, this is Mr. White.
Mr. Johnson.